Hello, good morning. So, welcome to the morning plenary session. And today we have a special focus on loop quantum cosmology with two speakers that are well known in the community and they are experts in this, let's say, part of our field. The first one is Parampreet Singh from Louisiana State University, and he's going to talk to physics of loop quantum cosmology, new answers to some old questions. So whenever you want, Param.
Thank you, Guillermo. And I'm really grateful to John and Mushin for the invitation to give this talk. I was given instructions by the organizers that I have to give an overview. Somehow, various talks of loop quantum cosmology have already happened in the parallel session, but I still hope like this talk would still be very useful for the coming talks, and especially to the younger audience. So I'm going to talk about some of the old questions which have been there, and I've picked up just two of the questions, and I'll try to provide like new answers to some of those old questions. These works, the work I'm going to talk about are based on works which I've done with my postdoc Baofi Lee, now who is a faculty in Hangzhou, Mason, who is a PhD student, Eklavya, like who finished his PhD at LSU, and Sahil Saini, who was my PhD student and now a faculty in India. Okay, so the motivation, let's start from that. Like we know that singularities such as the Big Bang, they are the limits of the validity of Einstein's beautiful theory of GR. And that is why incorporating quantum gravity effects is extremely important to resolve these singularities. And the fundamental question we want to understand is how does the quantum nature of gravity resolve the singularities and affects the physics of the early universe? The main lesson from LQG, which is used in LQC, is that the classical differential geometry, which we have in GR, is replaced by quantum geometry. And the cosmological and black hole spacetimes, they provide, as symmetry reduced models, they provide very tractable tools to understand the technology of loop quantum gravity, to implement those ideas rigorously, and to extract physics. So we have to remember that loop quantum gravity does not immediately lead to loop quantum cosmology. There are several assumptions, various simplifications which we make in the process. But still, loop quantum cosmology is a very rigorous mathematically as well as phenomenologically. And there are various important results that the singularities are generically resolved in the effective dynamics. The bounce is replaced, the Big Bang is replaced by the bounce in the Planck regime, thanks to like sophisticated numerical simulations which have been done, effective dynamics which has been tested rigorously, and so on. And there are many potential signatures in CMB which have been explored. So the goal of this talk is to step back and explore some non-trivial consequences of various quantization choices which we have made in the process, and how do they affect the physical implications. And this is where like sometimes my research is focused on trying to test the robustness of physics of loop quantum cosmology, attacking from different sides, whether one quantization ambiguity or regularization ambiguity gives different results. And at least to me, there were some surprises, some new, some old, and so on the questions. So I'd like to share some of them with you. So this is the brief outline of my talk. I was asked to give an overview, so about 40% of the talk will be an overview. And there is an important reason for that. And I'm so happy to see lots of young students and postdocs who are interested in applying seeds of loop quantum cosmology to spin form cosmology, to group field theory cosmology, and to spherically symmetric models and so on. But it's also important that it's like loop quantum cosmology is a huge machine, like which has many moving parts, and like it's just not the modified Friedman equation which we so comfortably use now. So I want to go through like lot of people's work which has been done, beautiful work. I'll at least try to mention what are the different parts of that machine. I'm going to talk about later on in the talk on quantization ambiguities, and I'm sorry, like I use this unfinished business because I'm trying to be a registered parliamentarian this summer. So it is truly an unfinished business because there was a topic which was laid on the table like long time ago about a quantization ambiguity, about the assignment of loop areas in anisotropic models. I want to bring it back, and I want to show you that it still had many useful lessons, and actually we can we can completely resolve that ambiguity in the anisotropic spacetimes. Then I'm going to talk about certain regularization ambiguities, which have been already talked about briefly earlier in the sense of the Thiemann regularization. And again, like there are certain surprises there from what we would expect from our intuition from loop quantum cosmology. I will talk briefly about distinct signatures. These were already discussed yesterday in Mason Mother-Herfer's talk. And something very surprising, which looks obvious, that can the universe be cyclic? Like this question may look meaningless to some of us that, well, we already have a bounce. It's easy to get cycles. Like what am I even talking about? But I will show you like it's a non-trivial question if you come from loop cosmological sector. And then I will conclude with some summary. Okay, so what is loop quantum cosmology? So very briefly, we essentially symmetry reduce the connection and triads at the classical level and then loop quantize the geometry. Various kinematical features of loop quantum gravity, they are exported to loop quantum cosmology thanks to preliminary early work by Martin Boyewald and this mathematically beautiful work of Ashtaker, Boyewald, and Lewandowski. Now, rigorous quantization of one of the first spacetimes was done in the APS model in 2006, and there it was shown that the Big Bang is replaced by a bounce. But after that, the results have been generalized to various spacetimes in different directions. And these are just some of the highlights. Like there are groups who have worked on various mathematical aspects of loop quantum cosmology, trying to look at the self-adjointness, physical Hilbert space, properties of the Hamiltonian constraint in great detail, and so on. The quantization of isotropic, anisotropic, and polarized Gaudi models, Gaudi T3 models, has been done in great detail. The Gaudi model so far we have for quantized, like the hybrid quantization, but I'm very hopeful that we will at some point also have a fully loop quantized models. We have beautiful works trying to connect loop quantum cosmology with loop quantum gravity, especially like FAU is one of the Makkas of all that work, where a lot of work has been done trying to understand the approach to loop quantum gravity. Independently, like the physics and mathematics of the cosmological sector from loop quantum gravity has been derived by various people from different directions we have tried to understand, and these are kind of complementary to each other. Now, most of the papers on loop quantum cosmology, and I think I stopped counting after 1,000 couple of years ago, they are on the effective dynamics, where the effective dynamics is assumed, and then people start understanding the phenomenology as in cosmological models. And I'm putting these names in red because these are well-known names in cosmology or string cosmology. These are not loopy people, but they have, and I think like we should be really, really happy that people like Copeland, Roy Martins, Shinji Tsujikawa, Alex Willington, they have all contributed to the development of this field. And there are many from our own field, which I have not mentioned here. Then there are also a lot of people who have developed sophisticated numerical techniques, and some of them are numerical relativists like Daniel Cartin and Peter Diener, who have also developed Einstein toolkit and so on. And then there are many approaches on perturbation, and I will briefly mention about them. So there are, as I was saying, there are lots of, and I probably have still missed some moving parts, but these are lots of moving parts which feed into each other. And the loop quantum cosmology is built on all of these pillars, not just one equation. Okay, so what is loop quantum cosmology? Briefly, its an evolution is determined by the quantum difference equation, arises from expressing field strength of holonomies computed over loops in the quantum geometry. One of the earliest models is the Ashtager-Pavlovsky Singh model in 2006, where if you start from a massless scalar field in spatially flat isotropic universe, then it leads to this difference equation where C plus C0, C minus are difference operators or eigenvalues of the difference operators. They have complicated expression, but doesn't really matter. You can write the whole physical Hilbert space, self-adjoint observables and Dirac observables and so on, and you can do what you can fully do in any quantum theory. So the main result is this, that if you plot the volume of the universe versus the relational time, which is given by the massless scalar field, and you plot the amplitude, and if you start somewhere from here, like let us say in the present macroscopic universe, if you take a state, evolve this state backwards, it bounces instead of going into Big Bang and latches onto a contracting branch on the other side. This is what is the, this shows the loop quantum cosmology with the effective description. The same plot, volume plotted versus phi. The red dots with the fluctuations are the coming from the full quantum difference equation. And then the blue line, which matches beautifully on those points, is the effective dynamics. And this effective dynamics has been tested extremely rigorously for a wide variety of states using high performance computing. The main idea is that the Big Bang is replaced by a bounce at a rho max, which is given by 3 by 8 pi g lambda square, where lambda is the edge length where you are taking the loops. This is given by 0.41 rho Planck. There is no tuning parameter here. This density is the supremum in the physical Hilbert space for this particular model. So you cannot have states which have higher density than this. It also implies then that there is a minimum expectation value of the volume. So even if you don't believe in this numerics, you can exactly solve this model and you can see the bounce. So not only about the expectation values or the supremum, but you can actually compute the consistent quantum probabilities as in the generalized quantum mechanics of Hartle and Ohms and Griffiths and so on. And the probability of the bounce turns out to be unity. And then, like as I was mentioning, this whole approach of the effective dynamics has been rigorously tested, including for anisotropic models. So you can comfortably believe in it, but that will be the assumption I'll be making. This has been tested for few models only. That's what we always have to remember. I think we have to still generalize to as many models as possible. But as everyone makes this assumption now, I'm going to make an assumption. Effective dynamics is valid, and then we are going to analyze the things from there. Okay, so some main results, and I classified them in 3 categories. That's my prejudice. First of all, if you assume the validity of effective dynamics, then all strong curvature singularities are resolved in all isotropic Bianchi 1, Bianchi 2, Bianchi 9, and Kentowski-Sachs spacetimes. There are many papers on trying to quantify observable signatures in CMB. First of all, there is an excellent agreement with observations for different inflationary models, both phi square and Starobinsky, and I think one more has been studied. There are slightly different approaches from one another, but like there is a consensus that irrespective of what approach or what quantization ambiguities we are talking about, there is an excellent agreement. Not only that, I think a very beautiful thing is that there is a potential explanation of anomalies if you choose some very well motivated initial states, or if you include non-Gaussianity. So this is a beautiful, rich area in which a lot of work has been done. I think like it has to be mentioned that even though this does not fall into loop quantum cosmology, a lot of progress of the resolution of the Schwarzschild singularities and spherically symmetric models in recent years is inspired from loop quantum cosmology, especially because the Schwarzschild interior is like a Kentowski-Sachs spacetime. It can be loop quantized. And then the ideas of loop quantum cosmology or the techniques we have learned in Schwarzschild spacetime and in gravitational collapse, they are being continuously to be implemented in spherically symmetric models. And yesterday's first 3 talks were talking about all of these things. Okay, so a lot of progress has been made. Lots of moving parts are there. The results are in these 3 categories, and I'm sorry like if I missed some particular category. But like there are some old questions, and I want to go back to these old questions. We have been answering these questions again and again since 2006, but there are still some new answers to these questions. The first question is like, what about quantization ambiguities? We were talking about this APS model, but there were earlier approaches. There were many other possibilities. So what about these quantization ambiguities? And can they be ruled out phenomenologically? And some of my friends here would say, yeah, we already know the answer. The answer is yes. They can be ruled, all of them can be ruled out phenomenologically. But I would try to revisit that and the lessons new lessons which we have learned from that. Secondly, like if we talk to people outside our community, they always ask, well, you have this bouncing model. But there have been earlier approaches like pre-Big Bang scenario of Gasparini and Manziano. There have been cyclic models of Steinhardt and Turok. Yes, they have lots of constraints. They're observationally not favored, but they also have singularity problem. And can loop quantum gravity approaches resolve the singularity problems of these models? And again, like some of my colleagues here will say, yes, we know that answer. Answer is yes, we can resolve their singularity problems. Let me refine these questions a bit more, add some new questions here to those old questions. And the new questions are in the red. I would also like to ask, even if we have quantization ambiguities, do they result in distinct signatures? And with that, probably like it means like the angular power spectrum or something in the CMB. Can we see that can we really go to such a precision theoretically and phenomenologically that we can really start confronting quantization ambiguities now with observations? That's the goal here. Then in these quantization ambiguities, I'm going to talk about two things. That first, that unfinished business, revisiting a loop area assignment ambiguity. I know that we know the answer, probably like what we will wish to come out, and we will see how it comes out, but sometimes the journey is much more important here. Then I will talk about the regularization ambiguities, which will be essentially standard LQC, which we know from Stecker, Boyewald, Lewandowski paper and papers developed on that. And then like what was in Yong and collaborators' papers was forgotten, reappeared after Dapper and Ligner's work, and so on. And we would like to see like whether these ambiguities leave a trace, which we can probably observe. That's essentially our goal, right? Like we don't just want to do standard LQC, but we want to see like the robustness of standard LQC physics and try to see like if there are versions beyond standard LQC, how do we see them potentially in observations? That's what we want to see. There have been earlier paradigms of bouncing and cyclic models, yes, but as I mentioned, these are under very, very tight constraints. So there are two options which we have on table. Like the two questions which can be asked. If we can resolve singularities, then can loop quantum cosmology effects help them to make them viable observationally? Or is there a way that we can just rule them out? These are anyway not favored models in the present scenario. So is it possible that probably there is an approach in loop quantum cosmology which just says, well, this particular paradigm does not fit with loop quantum gravity at all, so we can just forget about it. That would be really beautiful. We haven't seen that happening so far in standard loop quantum cosmology, because standard loop quantum cosmology is it's a non-trivial but still a simple symmetric quantization which only quantizes geometry, does not do anything to matter. So it will be difficult to see like how it comes out, but I will show you it does happen, that we can actually make a strong statement here. Okay, so let me go back now to the quantization ambiguities, and this is some of all of these things are on archive or going to be archived in a week, but maybe these are new to many of you, so I'll go through them. So in the isotropic models, the ambiguity is related to the assigning the minimum loop area, which means that when you're trying to shrink the area, you have to assign the area of the loop, whether you take it to the coordinate area, which was done in earlier papers by Boyewald, or you take the physical area, or you do the lattice refinement, and so on. All those things, they are severely restricted in isotropic models thanks to many directions which we have taken. You can take like the physical arguments, which Alex and I made from the independence from fiducial structures, classicality at late times, what happens when you have strong energy condition violation, and so on. If you do that, then you can rule all of them out. And later on, like John Engel and his student, they did a beautiful work, very mathematically, and they got the same result. So there is actually a unique quantization in the isotropic model, and that is what is called the mu bar scheme. But if you generalize, then you go to the anisotropic models, which are Bianchi 1, Bianchi 2, and Bianchi 9 models. If the spatial topologies are cube, then there is a single choice. There is only one choice, which mathematically works. And this was the approach which has been pioneered by Ashtaker and Wilson-Ewing. And I will call this as mu bar I scheme or mu bar scheme. And in this mu bar scheme, the mu bar, if some of you recall, this mu bar scheme in the isotropic model goes as 1 over square root of the triad. This is going in this particular, I think like I made a typo here. This should be in the denominator. So this still goes as 1 over square root of the triad. The interesting thing is that the mu bar scheme of the isotropic model, if you think in terms of the scale factor, it goes as 1 over the scale factor. And in this scheme, it goes as 1 over the directional scale factor. So in that sense, they are very close cousins of each other. So the main message is, if you have a spatial topology which is R3, there is only one scale. However, for example, you want to do Gaudi T3 models, or if you would look at the earlier literature of Wheeler-DeWitt quantum cosmology, where there are 3 torus and so on, then there is an earlier possibility. And that earlier possibility was first given by Davi Chow and they later pioneered by the Madrid group. And that's what I will call as a mu bar I prime scheme, which actually is very similar to the isotropic case. In the isotropic case, mu bar goes as 1 over square root of p. And what Davi Chow did was he did mu bar I going as 1 over the directional triads. And this scheme is not valid in R3. This scheme completely fails in R3. You can't even do it because it's not independent of the fiducial structures. Now you may take a viewpoint here, well, if it is not valid, like then why even look at it? But the point is that we also want to understand if you go to different topologies, do you have different choices or not? Anyway, there are still some important lessons here. So first of all, both choices result in mu bar scheme in the isotropic limit. So the isotropic limit of both the schemes is correct. On the other hand, there is a singularity resolution and recovery of large volume universe after the bounds for both. So for both the schemes, singularities are resolved and you get large volume universe after the bounds. Energy conditions are not violated anywhere in loop quantum cosmology. This is standard loop quantum cosmology. That is why when Chow and Vandersloot, they first looked at these both schemes, Chow and Vandersloot concluded from this large volume argument that both the schemes give you classicality, and that implies in Bianchi models, Bianchi 1 models, that the shear is conserved. So they looked at the shear. You can look at their paper. They plot the shear. It looks constant. They argued, well, energy conditions are not violated. So this is going to be classical. So mu bar I scheme, which is actually like the Ashtaker-Wilson-Ewing approach, results in universals bound on shear. So this is very beautiful aspect which comes. That's very similar to the universal bound of energy density, which also appears. Immediately leads to strong curvature, singularity resolution, and so on. But you can also do the same exercise here, though it has never been published, but you can do it. You will still get resolution of strong curvature, singularities, and so on, but not universal bounds. It is topology free. It has all these nice features. That is why it is community's preferred choice. And that is why I said it's a forgotten choice, the other one, because once it came up with these nice properties, it was preferred. But on the other hand, the mu bar scheme of the Bianchi 1 models is extremely complicated to quantize. On the other hand, like the mu bar prime I scheme is much simpler. It's very tractable. It's beautiful to quantize with even all these features. So why I got into all this? Like with one of my students, I was trying to understand phenomenology of the Bianchi models with magnetic fields. And I wanted to check the robustness. And my student who is sitting here, Mason, like asked me lots of why questions, like why we do this, why we don't do this, and so on. And at some point when I failed in convincing him to, well, because Vandersloot's paper says that, so we should probably believe it. Like I thought like, okay, let's do it and let's fix it and see like what is a phenomenology. So I was very, very surprised what we found. So one of the important features of Bianchi models is that in classical Bianchi 1 spacetime, if you take matter which has vanishing and isotropic stress, which means dust, radiation, massless scalar, inflaton, aperiodic potential, whatever you want, except magnetic field. Magnetic field doesn't have a vanishing anisotropic stress. But if you take matter which has vanishing and isotropic stress, an isotropic shear is conserved. That's a fact of the Bianchi 1 spacetime. That's a fact of the Bianchi 1 LQC also, if it is classical. So we did lots of simulations. So here in this figure, I'm plotting the Ashtaker-Wilson-Ewing scheme. I'm plotting the anisotropic shear before the bounds and anisotropic shear after the bounds. And you can see the beautiful agreement. They agree. Whatever you start from a fixed volume late at very early times, and these are about 500 simulations, which means each dot is a simulation of a complex Bianchi 1 universe. Both of them have been done on high performance computing. But you can see a beautiful diagonal here, which means that in the Ashtaker-Wilson-Ewing model, there is absolutely no issue of the conservation of shear across the bounds. Now, if you look at this model, which is the Chow's first model, which Madrid Group pioneered, if you look at the low anisotropies, it's falling on this diagonal. But if you look at large anisotropies or slightly larger anisotropies, and this is 10 to the power 8, it's deviating from the diagonal and it's actually going somewhere else. So I was very suspicious of these results, and I initially Mason obtained this in a Mathematica code. I didn't believe it because I thought like Chow Vandersloot paper I have gone through many times. I've done analytical calculations, but I was always focusing on this small regime here, the low anisotropy regime here. I was never looking at the high anisotropy regime analytically because it's so complicated to look at analytically. And then he wrote a sophisticated code, run on HPC, and then he convinced me, well, it's not conserved. And then I was very puzzled, like why it's not conserved. So shear scalar is not preserved across the bounds for large class of initial conditions for the mu bar prime I scheme or the Chow's first scheme. And this effect is very difficult to observe for lower anisotropies. That's why it was undetected. That is why Chow and van der Sloot claimed, well, this is classical. This gives classicality on the other side, macroscopic universe, but classical. Now the fun part is it is a macroscopic universe, no doubt, but it's not classical. And we will see now why it's not classical. So the shear problem of mu bar I scheme arises because one of the connections never becomes classical after the bounce. So this is the Ashteker-Wilson-Ewing scheme. It's the mu bar 2, C2 starts from 0, bounces, and goes to minus pi. That's what we expect, 0 to minus pi or pi to 0 and so on to get classicality. But you can see the same, what is happening with the other scheme. It starts from the same initial conditions. It never reaches the other classical side. It remains quantum throughout. So even though the universe becomes macroscopic, it's not classical. And I would like to give this as an insight to the younger audience. You may get a macroscopic volumes on one side of the bounce or so on in whichever scheme you are trying to work with. That does not imply classicality. There are still many checks we have to do for classicality. So interesting thing is, this is spatially flat. This is Bianchi 1. There is no recollapse. But even in this model, if you take just the classical dust, this model has a cyclic evolution. Very similar to what was happening in the mu naught scheme actually. So we can now safely rule it out. So we don't have to make any preferences that we prefer this because this happens, this is free of topology and so on. We can now physically rule out explicitly that there is, and we can say that there is only one scheme, as there is an isotropic model. There is only one scheme which works in isotropic models. And that is what was first given by Chow, van der Sloot and pioneered by Ashteker-Wilson-Ewing paper. So that's a good news. So now let's move on. Now I'll go to the second set of quantization ambiguities. And we have heard about this earlier. And like the father of this is there, Yong Ma, who did this actually in the audience. So Yong Ma in 2009 was exploring things beyond standard LQC. And he noticed that there are two terms, the Euclidean and Lorentzian terms, which the Ashteker, Boyewald-Lewandowski paper they had combined before quantization. And Yong Ma thought like, okay, what if we treat this Lorentzian term as is in the Thiemann regularization, in Thiemann and Christina and Thiemann's papers earlier. So there are two approaches, and it's important to notice the difference of the two approaches. The first approach is the main approach. That's the true higher of the Thiemann regularization. The other one is like some stepchild in a way. So the first approach is quantize this Lorentzian term using identities on the classical phase space and express in terms of holonomies. This is closer to LQG. This is what is the QSD papers actually say. That's how you do it. The second approach which Yong Ma did was, he said, okay, this is spatially flat, right? So in the spatially flat, there is no difference between extrinsic curvature and Ashteker connection. So let's just put K's in this term in terms of the Ashteker connection and then do the same thing what we do in LQC. And this, let's call this as MLQC1 and this as MLQC2. M stands for modified. And 1 and 2 stand for version 1 and version 2. We have to remember MLQC1 is a real Thiemann regularization. Okay, so in Thiemann's regularization, the Hamiltonian constraint one finds leads to an emergent de-Sitter pre-bounce phase in MLQC1. So I'm plotting these three curves. The red curve is LQC. The green curve, which looks very similar to LQC, is MLQC2. And the blue curve is MLQC1. That's a true Thiemann regularization. Like there is an emergent de-Sitter on this side, and there is a very similar to LQC on this side. All strong curvature singularities are again resolved in both MLQC1 and MLQC2. There are inflationary attractors you can find for both. So it's compatible with inflation. And in the pre-inflationary epoch, the post-bounce evolution very quickly agrees with LQC. So within few Planck seconds, there is absolutely no difference between LQC, MLQC1, and MLQC2. It appears here in the volume plot, but if you look at energy density, curvature, and so on, that there is absolutely no difference within few Planck seconds, and in less than 5 Planck seconds, everything lasts. Effects in primordial power spectrum were explored, first by Ivan, and then later on, and Boffey's talk on Friday will go into more details of that. And the consensus here was that, yes, there are probably differences, but they are not in the ultraviolet regime. They are hidden in the infrared regime and the intermediate regime. Okay, but we analyzed the angular power spectrum recently. And this is the angular power spectrum from the hybrid approach, and I will show you for the dressed approach also. And what we found is, so what we are doing here is, we are comparing these three models, LQC, MLQC1, MLQC2 for Starobinsky inflation. We are demanding that all three models give the same number of E-foldings, and we fix that E-foldings to 65. We are also demanding that the departures from three models from the observations is less than 1% in the scale invariant regime. So what we are trying to do is, let there be these three models, and let's hope that all three models fit with the scale invariant part of the spectrum. And we find something very surprising. What we find is that MLQC2 seems to be completely ruled out. It's giving a huge power amplification, and this is for adiabatic states and the hybrid approach right now. I'm not taking any specially motivated states. That's a project which people should do. So this is like going back to the few years when we were not doing with this low energy states or special states and so on. No non-Gaussianities, there's simple hybrid quantization, second order at this stage and so on. And you can see that MLQC2 is really a very bad fitting with observations. And probably we can already say that, well, it's bad news for MLQC2. There is a competition between MLQC1, which is this black line. The green line is lambda CDM. Black line is MLQC1. And red line is LQC. The results don't change if you do the dress metric qualitatively. We showed earlier, these are basically at a practical level just two sides of the same coin. So the results should not change, and we see like MLQC2 is still very bad. It's pretty bad, ruled out completely. We are now really ruling out quantization ambiguities from observations. And you can then still see there is a competition between LQC and MLQC1, but they are within the error bars. So the jury is still out who wins or not. But again, like this is still the first step towards this understanding. Okay, so now let me go to another fun part, like the cyclic models. So the conventional wisdom in classical cosmology and also in quantum cosmology is that the cyclic models are really straightforward to construct with negative potential or positive spatial curvature if you take care of the singularities. The problem of construction of cyclic models is only singularities. If you ask anyone in cosmology community, they will say, if you can resolve the singularity, you are done. It's super easy to construct a cyclic model. And well, this is a sophisticated exercise which took a year when I was in Penn State with Abhay, Kevin Vandersloot, and my dear friend Tomasz Pawlowski, where we are showing that if you take a k equal to 1 model, then the Big Bang, Big Crunch singularities are resolved. There is a recollapse here because of the spatial curvature, and the universe can cycle. And Thomas' code proved that you can do it for 10,000 times without even losing a bit of accuracy of effective dynamics and fluctuation and so on. There is no violation of any energy conditions, and it just keeps on oscillating. So this is a proof of that conventional wisdom. Now let's go to spatially flat models where this talk is focused. In the spatially flat models, again, this is an easy exercise. In the spatially flat universe, take a negative cosmological constant or a negative potential, add to a matter density which does not violate strong energy condition. That means it has 8 pi g by 3 rho, which is the normal matter, minus rho lambda, and then you will easily get recollapse, and there will be a big crunch which you can resolve, and it will keep on oscillating forward. In fact, Elisa Bentivigna and Tomasz Pawlowski in 2007, they did the complete quantization of this in LQC, and they showed, well, it goes through infinite cycles. Similarly, you can also study ekpyrotic and cyclic models. And we have done a lot of work, including Ed. We have done a lot of work to show that ekpyrotic models, which are cyclic, which should be cyclic, that's what Steinhardt-Turok hypothesis is, but they are not able to resolve the singularity. And using the same ideas, it has a negative potential. Using the same ideas, we can always resolve these singularities. And there was also very nice talks by Rachel Brown and Emmanuel Frion yesterday from different approaches, loop quantum cosmology and from what Francesca is doing on the same things. So singularities are resolved, but the problem of viability does not go away. Like Ed has tried very hard. We have been trying very hard. The spectrum is still not scale invariant after quantum geometric corrections. So that is a different story that we cannot make it viable. But the interesting story is something else. The interesting story is that if you don't do standard loop quantum cosmology, but if you do Thiemann regularized LQC, which is now MLQC1 we are talking about. We already ruled out MLQC2. If you look at MLQC1, there is no cyclic model possible. It just you don't even have to look at the observations. It's not dynamically viable. It's not possible. You can't embed it at all in that approach. And this is what I show here. The blue curve is Thiemann regularized LQC. The red curve is standard LQC. This is a negative lambda, and you can see like in standard LQC, there are oscillations and so on. There are cycles and so on. But in Thiemann regularized LQC, remember there was an emergent de Sitter phase in the past. There was a bounce, there is a recollapse, but after the recollapse, what happens is there is an emergent phase in the future. So it goes from one emergent phase to the next emergent phase. It goes from de Sitter to de Sitter, and there is just a small universe living in the middle. Aperiodic potential is shown here. LQC cycles, but Thiemann regularized LQC has no way it can give aperiodic or cyclic universes. It's not only for the negative lambda or aperiodic potential. The nature of Thiemann regularized LQC is that cycles are just impossible unless the negative potential you are using or the negative lambda you are using is itself Planckian. Basically, you have to kill this emergent de Sitter term somehow, and to do that, you have to introduce a negative lambda, which is really, really very, 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 very heavy. So it just completely rules out by design. So some nuances. Can quantization ambiguities be ruled out phenomenologically? Yes, we knew that. Do they result in distinct signatures? I think we can say yes. A forgotten loop area assignment ambiguity, so I brought it back, not classically viable. We showed that, as earlier believed, ruled out, but it gave useful lessons. And the useful lesson, for at least for me, was try to understand the entire, as much bigger parameter space as possible when we are trying to believe in models or rule out models. You do not know where the surprises may be. Like Chow Vandersloot did not see beyond small anisotropies, and even I did some numerical codes with small anisotropies, and even I didn't understand that. It was only when we used the power of high performance computing to really go to very high anisotropic universe, then everything revealed itself. So just doing one or two simulations is not enough. Regularization ambiguities, I think we can convincingly say MLQC2 is ruled out. We can just throw it out from the discussion. And MLQC1 seems promising. We don't know whether it's more promising or not, but it seems promising. Does quantum geometry effects help in resolution of singularities? Yes, we knew that. Since such models are restricted observationally, does LQC make them viable? Not so far, not for the choices we have made, but maybe there are some variants of these potentials, and maybe introducing new fields, it's possible. Are there any other constraints which rule them out? Yes, if Thiemann regularization is correct, there are no cyclic models for spatially flat universe. No cyclic models at all. No cycles at all are possible. And in fact, we can say that if there was a choice between inflationary and cyclic models and alternatives, standard LQC is kind of neutral. It doesn't take a stand. It says, okay, I will take whatever you give me, and we will see in the observations what happens. Thiemann regularized LQC is actually more aggressive. It says, well, if you give me two alternatives, inflationary paradigm is the way to go because I cannot embed any cyclic models in this approach. So this is the summary and some lessons. So I hope, I have given you an overview which shows that we have a platform to extract rigorous physics at Planck scale. There are still many assumptions we have made, but there is progress. Non-singular dynamics, extensive phenomenology has been studied. Many robustness checks have been done in last 20 years by many, many groups. There are well-justified quantization ambiguities which at first sight might seem like standard LQC, like in MLQC1. But they can result in very different physical implications. So we have to keep our eyes open for all of the possibilities. Some lessons, these are my lessons, and I'm just sharing them. Recovery of macroscopic universe is not enough for classicality, even when energy conditions are satisfied. You have to really formulate precise classicality requirements and test them before we declare victory. We got GR. We may not have got GR just because we have a large volume universe. Here we have to explore wide range of parameters as much as possible. And that is where phenomenology has to marry numerics or computational physics. Otherwise, the progress will be very slow, or probably like we'll go back and forth again and again. We have to consider different types of matter. This was not there in standard LQC. Standard LQC, again, was neutral on this. It was such a robust, simple quantization. But we see in theme and regularized LQC now, if you take inflationary potential, well, nothing happens really fun. But the moment you go to negative potentials, things start changing radically. So the matter does matter. I think like we can start saying that. We cannot be just neutral to matter anymore. Quantizations beyond standard LQC are complex and rich. And one of the talks, Yongima's talk yesterday, again scared me, like he was coming up with a new set of family of quantization ambiguities. But that's all very beautiful in a way. That is where the opportunities are. There are many, many opportunities. We have the blueprint from standard LQC, so we should just start applying in as many models as possible and trying to find the robust signatures of physics. I'll pause here.
So I'm actually curious, what is that lesson that we learned from LQC for the loop ambiguity in the loop assignment?
Sorry, so the lesson there was that if you remember the isotropic quantization, then there was earlier a mu naught scheme and mu bar scheme, right? So we knew like APS papers and what I did with Alex, mu naught scheme and all the lattice refinements were ruled out, only mu bar scheme remained. Now when you go to Bianchi 1 spacetimes, even in the mu bar family, there are two sets. You can do assignment in two ways. The first way Chow did was he used the same ansatz. Mu bar goes as 1 over square root of p. So he said, okay, I'm going to take mu bar going as 1 over square root of p for each of the directions. So this is within the mu bar, not two families of.
Okay, so this is ambiguity in the scale. In how is
exactly.
Okay,
how you assign the physical area of the loop.
Okay, but this is not really important for the full loop quantum gravity.
No, absolutely not. This is for the symmetry reduced models.
Okay, and then another comment, which is also from the point of view of the full theory. So there is some ambiguity which I think that you had in mind, but you didn't write it explicitly on your slide, which is that instead of the so-called this Lorentzian term in scalar constraint, actually we can write scalar constraint in terms of the Euclidean part and the Ricci scalar of the three-dimensional slice. Instead of this Lorentzian with different coefficients.
Yeah, so I think like I think probably we should discuss that. That will be probably MLQC3. So
and I think it could be also tested by the LQC
Absolutely.
models, which is.
I agree.
What differences?
Okay, I'm not aware of the physics of that, but I think it will be very interesting to see what happens.
Okay, thank you.
Thank you very much, Param. So I have this question. You said you used adiabatic states to show these results on the primordial power spectrum. Do you think that MLQC2 is still disfavored if you use some choice of vacuum that displays suppression in the infrared sector?
Yes, quite possible. So this is initial state dependent, but I would say like if you take adiabatic states, that's the look. I think like if we go into that game of cosmology, we can play that game very well, right? We have learned from cosmologists a lot, like we can change this and change that and so on. This was the simplest setting from what I learned from the dress metric papers and hybrid papers. Let's start from here. At this level, yes, you can see like MLQC2 is kind of in trouble, but probably like these non-oscillating states can resolve it. But if you use that same ansatz then on MLQC1 or LQC, they will be still a better fit. Maybe they will be explaining anomalies, right? So then we have to see like, we'll have to do this whole sophisticated statistical analysis and see. So this is a poor man's argument right now. I'm not an expert on statistical aspects of CMB, so I may still be wrong. But at least like naively, it seems to me that MLQC2 is in trouble.
Okay, thank you.
Yes, Ivan.
Thanks, Param, for this very, very nice overview. I enjoyed it. So I also have a question here because you make quite a strong point about MLQC2 being ruled out. My question is about what assumptions are behind this figure. Because, I mean, I imagine you assume inflation happens after the bounce. There is an inflationary potential that you choose. And more crucially, there is a choice of the length of inflation. And where quantum gravity corrections appear in that plot crucially depends on that choice. So my question is whether there are choices for which this model is not ruled out.
So we have taken Sterobinski inflation for this analysis. We have assumed that all three models give exactly the same number of e-foldings after their bounce happens for all three models. We have assumed that the departure of all three models, one by themselves, from the Planck data is less than 1% in the scale invariant regime. After that, we have explored like where we took the initial conditions before the bounce. We are not taking at the bounce, we are going before the bounce for all three models, taking into account whether the mass function square becomes negative or not, all those things into account. Even, and I'm only showing you one plot. Like we have done more analysis, trying to vary things. This aspect does not change. Yes, probably MLQC2 can be brought down a little bit, but this pattern remains. But again, like this is like still a first order work in that sense. The issue of anomalies, an issue of different states, issue of the whether we want what Monte Carlo simulations show is an open question.
Okay, I think we have to continue. So let's thank Parang again. Thanks.